Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Linear Second Order Differential Equations from paper Mathematical Tools for Materials. So students, let us see what we are going to learn in this module. First, the general linear differential equation of order n is described. Some general theorems about the existence and nature of solutions of linear differential equations are proved. The study is then specialized to second order linear differential equations. First, homogeneous equations are considered, then the Wronskian is introduced, and condition for linear independence of solutions is obtained. Then the specialization to homogeneous equation with constant coefficients is studied. Next, the inhomogeneous linear equations are considered. The method of undetermined coefficients for solving inhomogeneous equations with constant coefficients is described. Next, the method of reduction of order for solving inhomogeneous equation where a solution of the complementary equation is known is described. Finally, a very powerful method, that of variation of parameters, is described. Let me first introduce you to linear second order differential equations. We know that study of linear equations is particularly important. It is most thoroughly studied class of equations. It has innumerable applications in physics, applied physics, and material science. Second order equations are the most important in physics. Most classical physics reduces to the solution of such equations. We first study some general properties applicable to linear equations of any order. Most general linear equation of order n has the form P naught of x multiplied by y raised to power n plus P1 of x multiplied by y raised to power n minus 1 plus so on Pn minus 1 of x multiplied by y raised to power 1 plus Pn of x multiplied by y is equal to f of x. If right hand side is 0, the equation is homogeneous, else it is inhomogeneous. Now we define a differential operator given by capital D raised to power j. Now capital D raised to power j is equal to the jth order derivative with respect to x. Also d to the power 0, or I can say 0th order derivative with respect to x is equal to 1. Then in that case, function capital L of y will be equal to P naught into d to the power n plus P1 into d to the power n minus 1 plus so on Pn minus 1 into d plus Pn. The entire set of terms is multiplied by y and is equal to a function small f of x. Now we need to understand about the existence theorem. Assume pi of x and f of x that are continuous and single valued functions of x throughout some interval x lying between a and b, and that p naught of x does not vanish at any point in that interval. Now, the fundamental existence theorem for linear differential equations states that there exists a unique continuous solution y of x which assumes a given value y naught at the point x naught within the interval a to b and whose first n-1 derivatives are continuous and assume respectively the values y naught dash, y naught double dash and so on till the n-1th derivative of y naught at point x equals to x naught. So, the expression L is equal to P naught into d to the power n plus P1 into d to the power n minus 1 plus so on in Pn minus 1 to d plus Pn is called linear differential operator of order n. Here d refers to the differential operator. So, the differential equation given by function capital L of u equals to 0 is the corresponding homogeneous equation. It is called the complementary equation and sometimes the reduced equation. Now, we will discuss theorems that will describe some of the important properties of the operator L and the inhomogeneous and homogeneous equations respectively. First, if u of x is equal to u1 of x is a solution of the homogeneous equation, then so is c times u1 of x, where c is a constant. Let us prove it. Let us say ith differential operator d times c u1 is equal to c times ith order differential operator times u1. This implies LCU1 is equal to summation over I equal to 0 to n P of Pi d raised to power n minus I CU1. This is equal to C summation I is equal to 0 to n Pi d to the power n minus I U1 equal to C times L U1 equals 0. Second theorem, if u1, u2 and so on till um are n solutions of the homogeneous equation, then so is the linear combination given by c1u1 plus c2u2 plus so on till cm where ci are constants. We prove this theorem d to the power I multiplied by c1u1 plus c2u2 plus so on till cm is equal to c1 times d to the power I u1 plus c2 times d to the power I u2 plus so on till cm times d to the power I This follows L times c1 u1 plus c2 u2 plus so on till cm is equal to c1 times lu1 plus c2 times lu2 plus so on till cm times lum equals 0. If n linearly independent solutions of the homogeneous equation are known, then the solution u is equal to c1 u1 plus c2 u2 plus so on till cn is the complete primitive of the homogeneous equation. The n constants can be chosen by the requirement u of x naught is equal to y naught. The derivative of u at x equal to x naught is equal to y naught prime and so on. The n minus 1 derivative of u at x is equal to x naught is given by n minus 1 y naught raised to power n minus 1. The constants to obtain are unique since according to the fundamental theorem, with these conditions the solution is unique. Let y of x is equal to y naught x be any solution of the inhomogeneous equation and u1 a solution of the corresponding homogeneous equation. Then y naught x plus u1x is also a solution of the inhomogeneous equation. We can prove it simply as L times y0x plus u1x is equal to the product of L and y0x plus the product of L and u1x, which in turn is equal to f of x plus 0, thus resulting in f of x. Thus, it is proved that y0x plus u1x is also a solution of the inhomogeneous equation. Secondly, let y of x is equal to y0 of x be any solution of the inhomogeneous equation if ux is the complete primitive of the corresponding homogeneous equation. Then y0x plus ux is the most general solution of the inhomogeneous equation. The proof may be referred as L times y0x plus ux is equal to L times y0x plus L times u of x, which is given by f of x. Thus, y0x plus ux is a solution of the inhomogeneous equation, but the solution contains n arbitrary constants and hence it is the most general solution. The general solution consists of two parts. First, the complete primitive of the corresponding homogeneous equation. Second is the particular integral, which is any solution of equation and contains no arbitrary constants. We now refer to some examples from second order equations. First example, we consider the equation y double prime plus x square y equals 0. Here, p0 equals 1, p1 equals 0 and p2 equals x square. All these functions are continuous on the interval minus infinity to infinity. Hence, every initial value problem has a unique solution over minus infinity to infinity. Second, x square times y double prime plus xy prime minus 4y equals 0. Here, p0x is x square, which has a 0 at x equal to 0. Thus, we must consider the solution on either minus infinity to 0 or 0 to infinity. By inspection, y is equal to x square is one of the solutions of this equation, which is valid for all x. The other solution is y equals to 1 by x square. This solution is valid in minus infinity to 0 and 0 to infinity. Thus, y is equal to c1 times x square plus c2 divided by x square is the general solution, which is valid in the regions minus infinity to 0 and 0 to infinity only. Next, we proceed towards homogeneous linear differential equations. We will consider the second order homogeneous linear differential equation. If small n linearly independent solutions of the homogeneous equation of order small n are known, then we know the complete primitive. In the case of second order equations, we must know two linearly independent solutions. Functions y1 and y2 on AB are said to be linearly independent if given constants c1 and c2. Next, I'll introduce the Wronskian. The Wronskian provides criteria for linear independence. If y1 and y2 are two solutions of the differential equation given by y double prime plus p of x into y prime plus q of x is equal to 0 and p and q are continuous on the interval a to b, then the Wronskian W is given by y1 times y2 prime minus y2 times y1 prime. We now define the Abel's formula. Abel's formula states that W of x is equal to w of x naught multiplied by e to the power minus of integral of px dx within the definite limits x naught to x, where x naught belongs to the interval a to b. We differentiate the expression for Wronskian with respect to x and use the differential equation. So, w prime is equal to y1 prime times y2 prime plus y1 times y2 double prime minus y2 prime y1 prime minus y2 y1 double prime. This is equal to y1 times y2 double prime minus y2 times y1 double prime. The terms for y1 and y2 can be separated and we obtain the equation w prime is equal to y2 times within the brackets p y1 prime plus q y1 minus y1 times within the brackets p y2 prime plus q y2. This is equal to minus p times the Wronskian w. Thus, w is a solution of a first order equation that can be easily solved. The result is w of x is equal to k times e raised to power minus integral of px dx. This is equal to w of x naught into e raised to power minus integral of pz dz within the definite limits x naught to x. If w of x naught is equal to 0, then w of x is equal to 0. On the other hand, since the exponential function has no zeros, if w of x naught is not equal to 0, then wx has no zero in AB. The Wronskian is usually written in the alternative form of a determinant. Wronskian can be written as the determinant with the row vectors as y1, y2 and the next row as y1 prime, y2 prime. In this form, the Wronskian for a set of n functions of a real or complex variable is defined as the determinant w equals the determinant where the first row is given by the elements y1, y2 and so on till yn. Second row is given by the first order derivatives of y1, y2 and so on till yn, and subsequently the n-1th row is given by n-1th derivative of y1 and n-1th derivative of y2 and so on till n-1th derivative of y1. The Wronskian is defined for any set of functions. The non-vanishing of the Wronskian is a sufficient condition for the linear independence of the set of solutions, but not a necessary condition for linear independence of a set of functions. Now we consider some examples. First, we consider the equation y double prime minus 2 by x times y prime minus x raised to power 4 times y equals 0. In this equation, p of x is equal to minus 2 divided by x. This implies w of x is equal to k times e raised to power minus integral of px dx, resulting in wx being equal to k times x square. The Wronskian is 0 at x equals 0. Hence, two linearly independent solutions will exist in the intervals minus infinity to 0 and 0 to infinity. Another example, the equation y double prime minus 7 times y prime plus 10y equals 0. In this equation, px is equal to minus 7. Thus, w of x is equal to k times e raised to power minus integral of px dx will be given as k times e raised to power 7x. The solution of this equation are constant multiples of e raised to power 2x and e raised to power 5x. Hence, w is equal to y1 y2 prime minus y2 y1 prime is equal to k times e raised to power 7x. This verifies Abel's formula. Homogeneous equation with constant coefficients. We now consider the special case of linear homogeneous equations with constant coefficients. If a, b, c, where a is not equal to 0 are constants, then our equation is given by a times y double prime plus b times y prime plus cy equals 0. Obviously, in this case, solutions are defined on the interval minus infinity to infinity. So, we will not refer to the interval on which the solutions are defined. Since derivative of the exponential function is the exponential function itself, we try a solution of the form y is equal to e raised to power kx. Substituting this proposed solution in the above equation, we obtain the characteristic equation as a times k square plus b times k plus c equals 0. This gives k is equal to 1 by 2a multiplied by minus b plus minus square root of b square minus 4ac. Now, there are three cases to be considered. First, we consider the case where the roots are real and distinct. This is the case when b square minus 4ac is greater than 0. Let the two roots of the characteristic equation be k1 and k2. The Wronskian is then capital K times k2 minus k1 e raised to power k1 plus k2x, which is not equal to 0. Hence, the roots are linearly independent and general solution is given by y is equal to c1 y1 plus c2 y2, which in turn can be written as c1 times e raised to power k1x plus c2 times e raised to power k2x. We now consider the next case where roots are real and repeated. This is the case when b square minus 4ac is equal to 0. Since here we have only one root, therefore only one solution of the type e raised to power kx exists where k is equal to minus b by 2a. To find the second solution, we try y is equal to e raised to power kx times ux. This is equal to e raised to power minus bx by 2a times ux, where k is substituted as minus b by 2a. We may obtain the equation as a times y double prime plus b times y prime plus cy is equal to e raised to power minus bx by 2a. Then within the brackets we have a multiplied by u double prime minus b by a u prime plus b square by 4a square u plus b multiplied by u prime minus b by 2a of u plus c times u brackets close is equal to a times e raised to power minus bx by 2a multiplied by u double prime is equal to 0. Since the coefficients of u and u prime terms are both 0, therefore u is given as u is equal to c1 plus c2 times x. Solution y will be equal to e raised to power minus bx by 2a times c1 plus c2x. Since the Wronskian of these two solutions, e raised to power minus bx by 2a and x e raised to power minus bx by 2a is not zero, the two are linearly independent and we obtain the required general solution. Now we consider the third case where the roots are complex conjugate. This is the case when b square minus 4ac is less than 0. Let the two complex conjugate roots in this case be k1 plus I k2 and k1 minus I k2, where k1 is minus b by 2a and k2 is 1 by 2a multiplied by square root of 4ac minus b square. The general solution is therefore y is equal to e raised to power minus bx by 2a multiplied by a1 e raised to power I k2x plus a2 e raised to power minus I k2x. For real functions of real variables, we rewrite the general solution as y is equal to e raised to power minus bx by 2a times c1 sin k2x plus c2 cos k2x. Now we consider some examples. First, the differential equation y double prime minus 5y prime plus 6y equals 0. The initial conditions are given by at x is equal to 0, y is equal to 2 and at x is equal to 0, the first derivative of y equals 5. Therefore, k is equal to 1 by 2 multiplied by 5 plus minus square root of 1, which gives the value of k as 2 and 3. Hence, the general solution is y is equal to c1 times e raised to power 2x plus c2 times e raised to power 3x. Initial value problem implies c1 is equal to c2 is equal to 1, resulting in y being equal to e raised to power 2x plus e raised to power 3x. Another example, we consider the equation y double prime plus 4y prime plus 4y equals 0. Here, b square minus 4ac is equal to 0. Therefore, minus b by 2a is equal to minus 2. Hence, the general solution is y is equal to e raised to power minus 2x times c1 plus c2x. Another example, we consider the differential equation y double prime plus 2y prime plus 2y equals 0. The initial conditions are given as at x is equal to 0, y is equal to 1 and at x is equal to 0, partial derivative of y is equal to 2. We calculate the value of b square minus 4ac, which comes out to be minus 4, and the value of minus b by 2a is minus 1. So, the general solution in this case is given by y is equal to e raised to power minus x within the brackets c1 times sin x plus c2 times cos x. And the solution to the initial value problem is y is equal to e raised to power minus x times 2 times sin x plus cos x. Now, the inhomogeneous linear equation given by y double prime plus p of x into y prime plus q of x into y is equal to f of x, where f of x is not equal to 0. The existence theorem states that if p of x, q of x and f of x are continuous on an open interval AB and if x naught is any point in AB and if y naught prime are any two real numbers, then the initial value problem says y double prime plus p of x into y prime plus q of x into y is equal to f of x, where the boundary conditions are given by y of x naught is equal to y naught, and similarly the first order derivative of y at x naught is equal to y naught prime. This has a unique solution in AB if y1 and y2 are two linear independent solutions of the complementary equation and yn any solution of the given inhomogeneous equation. Then the most general solution of this equation is yn plus c1y1 plus c2y2. Then the most general solution of this equation is given by yn plus c1y1 plus c2y2. Now we proceed with some of the examples of the inhomogeneous linear equations. Y double prime minus y 5 times y prime plus 6y is equal to 6 is the differential equation. The initial conditions are given by at x is equal to 0, y is equal to 2, and at x is equal to 0, the first derivative of y equals 4. The solution of the complementary equation is given by y is equal to c1 times e raised to power 2x plus c2 times e raised to power 3x. By inspection, we see that y of x is equal to 1 is a solution of the above equation. Hence, the general solution is y is equal to c1 times e raised to power 2x plus c2 times e raised to power 3x plus 1. The solution to the initial value problem is y is equal to minus of e raised to power 2x plus 2 times e raised to power 3x plus 1. Another example where the differential equation is given by x square times y double prime plus x times y prime minus 4y is equal to 2 times x raised to power 4. The equation may be rearranged as y double prime plus 1 by x times y prime minus 4 by x squared times y is equal to 2x squared. Both px and qx have a discontinuity at x is equal to 0. So, the solution is to be found on minus infinity to 0 and 0 to infinity. By inspection, x raised to power 4 by 6 is a solution of the given equation. Adding to it the solution of the complementary equation, we obtain the general solution of the equation valid on minus infinity to 0 and 0 to infinity. Thus, y is equal to c1 times x square plus c2 times x raised to power minus 2 plus x raised to power 4 by 6. Next, we move on to discuss the principle of superposition. The principle of superposition states that if y1 and y2 are particular solutions of the inhomogeneous equations, y double prime plus px y prime plus qxy is equal to f1x and y double prime plus px y prime plus qxy is equal to f2x respectively, then ynx is equal to y1x plus y2x is a particular solution of the equation y double prime plus px times y prime plus qx times y is equal to f1x plus f2x. This is the principle of superposition. Let us prove it. The proof is trivial. Yn double prime plus px yn prime plus qx yn is equal to y1x plus y2 of x double derivative plus px times single derivative of y1x plus y2 of x plus qx times y1 of x plus y2 of x. This is equal to y1 double derivative of y1 of x plus px times the single derivative of y1 of x plus qx times y1x plus the double derivative of y2x plus px times the single derivative of y2x plus qx times y2x. This is equal to f1x plus f2x. Hence, the superposition principle is proved. This principle of superposition sometimes helps in finding a particular solution of an inhomogeneous equation. Next, we discuss the method of undetermined coefficients. In this method, we start with a trial solution containing certain parameters, put it into the given equation, and equate the two sides to obtain the values of those parameters. We consider equations of the form a times y double prime plus b times y prime plus cy is equal to f of x, where a, b, c are constants, a is not equal to 0. If Pnx and Qnx are polynomials of order n, then and f is a function of the type first Pnx. In this case, we take the trial solution of the form y is equal to x raised to power s times Qnx, where s is the number of times 0 is a root of the characteristic equation. Second, if the function f is of type Pnx multiplied by e raised to power alpha x, we take the trial solution of the form y is equal to x raised to power x Qnx e raised to power alpha x, where s is the number of times alpha is a root of the characteristic equation. Third, if the function f is of the type Pnx multiplied by e raised to power alpha x further multiplied by sine of beta x, or Pnx e raised to power alpha x into cos of beta x. In this case, we take the trial solution of the form x raised to power s Qnx into e raised to power alpha x into sine of beta x, or x raised to power s Qnx into e raised to power alpha x into sine of beta x. S is 1 if alpha plus I beta is the root of the characteristic equation and is 0 otherwise. Here are some examples that will illustrate the method of undetermined coefficients. Consider the differential equation y double prime minus 4 times y prime plus 3y is equal to e raised to power 3x times x plus 1. The fundamental set of solutions of the complementary equation is e raised to power x and e raised to power 3x. Roots of the characteristic equation are given by 1 and 3. So, s is equal to 1. Hence, yt is equal to x times a plus bx times e raised to power 3x. I differentiate this equation to obtain yt prime, which is given as 3ax square plus 2a plus 3b times x plus b. The entire bracket, all the terms are multiplied by e raised to power 3x. Similarly, the second order derivative of yt is obtained as e raised to power 3x multiplied by 9ax square plus 12a plus 3b times x plus 1. Putting these into the differential of equation above, we obtain y double prime minus 4 times y prime plus 3y is equal to 4ax plus twice of a plus b. Entire terms are multiplied by e raised to power 3x, which gives y double prime minus 4y prime plus 3y is equal to e raised to power 3x times x plus 1, giving the values of a and b as 1 by 4. Hence, the general solution of the differential equation is y is equal to c1 times e raised to power x plus c2 times e raised to power 3x plus x into x plus 1 by 4 times e raised to power 3x. This is equal to c1 times e raised to power x plus within the brackets c2 plus x into x plus 1 by 4 multiply brackets close multiplied by e raised to power 3x. Now we will study the method of reduction of order of differential equation. This job of finding a solution to the general second order inhomogeneous equation given by p naught x times the double derivative of y plus p1x times the first derivative of y plus p2xy is equal to f of x can be reduced to a solution of first order equation if one non-trivial solution y1 of the complementary equation is known. It is called method of reduction of order as it reduces the job to solving a first order equation. Unlike the method of undetermined coefficients, it does not require the coefficients pi to be constant or f to be of any special form. If y1 is a solution of the complementary equation, then p naught x y double prime plus p1x y prime plus p2x y is equal to 0. We try a solution for the inhomogeneous equation of the form y is equal to y1 times u. Then the first derivative of y may be obtained as y1 times u prime plus y1 prime times u. Similarly, the second order derivative of y can be obtained as y1 times u double prime plus 2 times y1 prime u prime plus y1 double prime times u. Plugging these into second order inhomogeneous equation, we have p naught x within the brackets y1 u double prime plus 2 y1 prime u prime plus y1 double prime times u brackets close plus p1 of x multiplied by within the brackets y1 u prime plus y1 prime u brackets close plus p2x y1 u is equal to f of x or p naught y1 u double prime plus u prime multiplied by within the brackets 2p naught y1 prime plus p1 y1 plus u multiplied by within the brackets p naught y1 double prime plus p1 y1 prime plus p2 y1. This is equal to f of x. Since y1 is a solution of the complementary equation, the coefficient of the u term is 0. Thus, the equation reduces to p naught y1 u double prime plus u prime multiplied by within the brackets 2p naught y1 prime plus p1 y1 is equal to f of x. This is the first order equation in u prime. Now we put u prime equals to v and u double prime will definitely be equal to v prime. Therefore, the differential equation is equal to given by p naught y1 v prime plus v multiplied by within the brackets 2p naught y1 prime plus p1 y1. This is equal to f of x. This is a first order equation in V. We can solve it and then integrate to obtain u, and eventually the solution given by y is equal to y1 times u. Now we consider some examples. Consider the differential equation xy double prime minus 2x plus 1 times y prime plus x plus 1 times y is equal to x cube. Given that y1 is equal to e raised to pi x is a solution of the complementary equation, then y is equal to y1 times u and u prime is equal to v. Here in this equation we can see p naught is equal to x and p1 is equal to minus of 2x plus 1. p2 will be equal to x plus 1. fx will be equal to x cube. So the equation becomes x times e raised to pi x v prime plus e raised to pi x times v multiplied by within the brackets 2x minus 1 is equal to x cube. So the y prime minus 1 by x times v will be equal to x square times e raised to power minus x. The solution to the complementary equation to this first order equation is y1 is equal to x. So we try a solution of the form v is equal to x times w. W prime will be equal to x times e raised to power minus x. So w can be obtained by integrating the equation, and w is equal to c1 minus 1 plus x into e raised to power minus x. V will be given by x times w. So v is equal to c1 times x minus x times 1 plus x multiplied by e raised to power minus x. U prime is equal to v and is equal to c1 times x minus x times 1 plus x multiplied by e raised to power minus x. I can integrate this equation to obtain u as c2 plus 1 by 2 of c1 x square plus e raised to power minus x times within the bracket 3 plus 3x plus x square. Finally, the solution y is the product of y1 and u and is given by e raised to power x times u. So y is equal to e raised to power x multiplied by c2 plus c1 x square divided by 2 plus 3 plus 3x plus x square within the brackets. This is the general solution of the given inhomogeneous equations. Thus we get the general solution of the given inhomogeneous equation. As a bonus, we have got the complete solution of the complementary equation as well as the general solution of the given inhomogeneous equation. Now we will consider another example. Consider the differential equation x square times y double prime minus 4x times y prime plus 6y is equal to x raised to power 5, where x is greater than 0. It is given that y1 is equal to x square is the solution of the complementary equation. So the solution y will be the product of y1 and u and is equal to x square times u. P naught in this equation is given by x square, p1 equals minus 4x, p2 equals 6 and f of x equals x raised to power 5. So the equation becomes p naught times y1 u double prime plus u primes multiplied by within the brackets 2p naught y1 prime plus p1 y1 is equal to f of x. So we get x raised to power 4 times u double prime is equal to x raised to power 5. So u double prime is actually equal to x, or I can integrate this equation to obtain u prime as c1 plus x square by 2. Will be equal to c2 plus c1x plus 1 by 6 x cube. I can say y will be equal to x square times u. So y will be equal to c1 times x cube plus c2 times x square plus x raised to power 5 by 6. So once again we obtain the complete solution of the complementary equation as well as the general solution of the given inhomogeneous equation. Next we discuss the method of variation of parameters. This is a very powerful method. It needs both solutions of the complementary equation. It is usually easier to apply than the reduction of order method, and also it can be generalized to higher order linear equations. If y1, y2 are the two linearly independent solutions of the homogeneous equation given by p naught of x into y double prime plus p1 of x into y prime plus p2 of x into y is equal to 0, then search for solutions of the form y is equal to y1 u1 plus y2 u2. So, the derivative of y will be given as y prime is equal to y1 times u1 prime plus y1 prime times u1 plus y2 times u2 prime plus y2 prime times u2. Now, to determine two unknowns u1 and u2, two equations are required. One equation is given by y1 u1 prime plus y2 u2 prime is equal to 0. We get y prime is equal to y1 prime u1 plus y2 prime u2. The equation can be differentiated to obtain y double prime is equal to y1 prime u1 prime plus y1 double prime u1 plus y2 prime u2 prime plus y2 double prime u2. Substituting these expressions for the first and second derivatives into the differential equation, we have p naught x times y double prime plus p1x y prime plus p2x y will become equal to p naught x multiplied by within the brackets y1 prime u1 prime plus y1 double prime u1 plus y2 prime u2 prime plus y2 double prime u2 brackets close plus p1x within the brackets y1 prime u1 plus y2 prime u2 plus p2x y. This equation can be further expanded to obtain p naught x y1 prime u1 prime plus p naught x y2 prime u2 prime plus u1 times within the brackets p naught x y1 double prime plus p1x y1 prime plus p2x y1 plus u1 times again within the brackets p naught x y2 double prime plus p1x y2 prime plus p2x y2. Now, since the coefficients of u1 and u2 terms are 0, so the RHS of the differential equation, which is f of x, will be equal to p naught x y1 prime u1 plus p naught x y2 prime u2. Thus, we get y1 prime u1 prime plus y2 prime u2 prime is equal to f of x divided by p naught of x. This is the second condition to be satisfied by u1 and u2. On solving equations for u1 prime and u2 prime, we obtain u1 prime is equal to minus f of x times y2 by p naught x times w. Similarly, u2 prime will be equal to f of x times y1 divided by p naught x times w. Here, w is the Wronskian of the two solutions and is given by y1 times y2 prime minus y2 times y1 prime. Since the two solutions are linearly independent, so the Wronskian is non-zero and hence p naught x is also non-zero. Hence, the denominator in the above equations is non-zero as well. On integrating the above equations, we obtain u1 to be equal to c1 minus integral of fxy2 divided by p naught x w dx, and u2 is equal to c2 plus integral of f of x y1 divided by p naught x w dx. Now we can obtain the general equation of the differential equation as y is equal to y1 u1 plus y2 u2. So we substitute u1 and u2 as calculated above and we get y is equal to c1 y1 plus c2 y2 minus y1 multiplied by the integral of fxy2 divided by p naught x w times dx plus y2 multiplied by the integral of f of x y1 divided by p naught x w dx. Now we proceed with some examples. We have the differential equation x square y double prime minus 2xy prime plus 2y is equal to x raised to power 5 by 2, where x is greater than 0. Solutions of the homogeneous equations are y1 is equal to x and y2 is equal to x square. So, the Wronskian w given by y1 times y2 prime minus y2 times y1 prime will be equal to x square. u1 will be equal to c1 minus integral of fxy2 divided by p naught x w times dx will be equal to c1 minus integral of x raised to power half dx, which results in giving u1 to be equal to c1 minus 2 by 3 multiplied by x raised to power 3 by 2. Similarly, u2 can also be obtained by using the expression u2 is equal to c2 plus integral of f of x y1 divided by p naught x w dx, which will be equal to c2 plus integral of x raised to power minus half dx. This gives u2 to be equal to c2 plus 2 times x raised to power 1 by 2. Hence, the general solution y will be equal to y1 u1 plus y2 u2. So, substituting the values of u1 and u2, we get y is equal to c1x plus c2x square minus 2 by 3 x raised to power 5 by 2 plus 2x 2 times x raised to power 5 by 2. This is further simplified to obtain y is equal to c1x plus c2x square plus 4 by 3 x raised to power 5 by 2. Now let us consider equation of the form y double prime plus y is equal to tan of x. The two solutions of the complementary equation are sine of 3x and cos of 3x. Therefore, we have y1 times u1 prime plus y2 times u2 prime to be equal to 0. So, sin x times u1 prime plus cos x times u2 prime will also be equal to 0. This gives u2 prime to be equal to minus tan x times u1 prime. Next, y1 prime u1 prime plus y2 prime u2 prime will be equal to f of x divided by p naught x. This implies cos x times u1 prime minus sin x times u2 prime will be equal to tan of x. So we get cos x u1 prime plus sin x tan x u1 prime is equal to tan of x. This results in u1 prime being equal to sin of x, or the expression is integrated to obtain the u1 to be equal to minus of cos x. Similarly, u2 prime is obtained as minus of tan x u1 prime. So u2 prime is minus tan x sin x, where u1 prime is substituted as sin x. So u2 will be equal to sin x minus natural logarithmic of tan within the brackets pi by 4 minus x by 2. Hence, the general solution is y is equal to c1 times sin x plus c2 times cos x minus cos x, the natural logarithmic of tan of within the brackets pi by 4 minus x by 2. So students, let us summarize what we have learned in this module. We begin this module with a description of the general linear differential equation of order n. We enunciate and prove some general theorems about the existence and nature of solutions of linear differential equations. After that, we specialize to second order linear differential equations, which is our main topic. We first deal with homogeneous equations. We introduce the Wronskian and obtain condition for linear independence of solutions. Next, we specialize to homogeneous equation with constant coefficients and describe special method for such equations. We then come to inhomogeneous linear equations, the method of undetermined coefficients for solving inhomogeneous equations with constant coefficients is described. Next, the method of reduction of order for solving inhomogeneous equation when a solution of the complementary equation is known is described. Finally, a very powerful method, that of variation of parameters, is introduced. Thank you students for your patience.